Hello guys, thank you for watching this video lecture. In today's lecture, we're gonna learn iterative deepening search. In the previous lecture, we learned about different branches of AI. We learned about problem solving by search. We learned about different categories of problem solving by search. And in the case of uninformed search, we already learned BFS, DFS, and today we're gonna learn iterative deepening search. Iterative deepening search, or simply IDS, and this is essentially a combination of DFS and BFS. The key idea is that it gradually increases the depth limit until a goal is found. At each stage, or you can say at each iteration, the IDS performs DFS up to a certain depth. Then it increases the depth limit step by step. This approach captures the best of both worlds. It benefits from the fast goal discovery of BFS while maintaining the memory efficiency of DFS. That makes IDS especially useful when the search space is very large and we don't know the depth of the goal node in advance. So to put it simply, BFS was fast. DFS was memory efficient, as we learned in the previous lectures. So IDS combines both by running DFS repeatedly, but in a BFS-like layered fashion. So the procedure of IDS works by combining DFS space efficiency with the shallow solution advantage of BFS. The procedure is simple. First, we run DFS with a depth limit of 1. If we found the solution, it's okay. Otherwise, we will increase the limit to 2. If that also fails, we increase it to 3, and so on, until the goal is located. At first glance, this might work wastefully redundant, since we seem to be re-exploring the same nodes multiple times. But in practice, most of the work actually happens at the lowest level of the search tree. Because of that, the overhead from repetition is relatively small if we compare it to overall efficiency that IDS provides. So here is one example to see how IDS works step by step. In the first iteration, the depth limit is 0. In here, the depth limit is 0, and we explore the root node, only A. If it's a solution, finish. Otherwise, we will go to the iteration number 2, and we will change the level to level 1. We expand one more level, and we will visit A, B, and C, right? A, B, and C. In the third iteration, with the depth limit of 2, the search goes deeper. Now we visit A, B, then D, then E, then C, then F, and finally G. In the fourth iteration, with the depth limit of 3, we go deeper and we will visit A, B, then D, then H, then I, then E, then C, then F, then K, and finally G. In this procedure, we learn how IDS systematically deepens the search. Each iteration restarts DFS, but by gradually increasing the depth, it ensures that if a shallow solution exists, it will be found first, while still keeping the memory use efficient. Iterative deepening search offers some important advantages. It combines the strength of both BFS and DFS, so it gives us the fast goal discovery of BFS along with the memory efficiency of DFS. This advantage makes it especially powerful when dealing with every large or unknown search depth. However, IDS also has a drawback. Each new iteration repeats the work of all the previous phases. Although this redundancy is not as costly as it first seems, since most of the effort is spent at the deepest level, it is still a limitation compared to the other methods. So, in conclusion, IDS strikes a practical balance between BFS and DFS. By gradually increasing the depth limit, it ensures that the shallow solution can be found quickly while still keeping memory requirements low. Although the process involves some repeated work, the efficiency gained at deeper levels far outweighs the overhead. This makes IDS one of the most effective uninformed search strategies, especially when the search space is large and the depth of the goal is unknown. Thank you for watching and see you in the next lecture.